Hello everyone. I'd like to welcome you all to SPEX CertiPrep's webinar on identifying and quantifying the uncertainty associated with instrumental analysis. I'm Peter Esco, the Marketing and Communications Manager here at SPEX CertiPrep, and I'll be moderating today. Before we begin, I'd like to get a few housekeeping items out of the way. First off, everyone here today will be sent a copy of the presentation slides. We'll send out an email later today with a link where you can download them. The webinar is being recorded, and we will post it on our YouTube channel so that you can watch it again at your convenience. It'll be uploaded in about a week or so, and you'll receive a follow-up email with the link when it's available. We do have a Q&A session at the end of today's event, so just type your questions into the question box as you think of them, and we'll get to as many as we can. With that out of the way, let's get on with today's presentation. I would like to introduce Vanuja Sivakumar. Vanuja received her PhD from the Department of Inorganic and Physical Chemistry from the Indian Institute of Science in Bangalore, India. She worked with Lever Brothers India as a research chemist for 9 years before coming to SPEX CertiPrep 20 years ago as our QA and regulatory manager. She is now our Vice President of Manufacturing. Vanuja, I'll pass it off to you.
Thank you, Peter. Good afternoon, everyone. Today's topic, as Peter mentioned, is identifying and quantifying the uncertainty associated with instrumental analysis. Calculating uncertainty is a mystery to all of us. I hope by end of this presentation, you get more familiarity with this calculation. So what are we going to cover in today's presentation? In the past, chemists focused on precision of results from any given method. However, these methods, it's not just enough to have a precise method. We have to establish the quality or accuracy of results by stating a measure of confidence. One useful measure is measurement uncertainty. Since precision, accuracy, confidence interval, and errors are fundamental in analytical chemistry, we will be covering them here only briefly. Our main goal for today's presentation is to explain about uncertainty in practical terms. We will be showing one of the ways to calculate uncertainty, taking into account the analysis of gold by ICP. We will calculate uncertainty associated with the measurements as applied to the process we have chosen. True value for the quantity measured depends on method, instrument, and operator. Any of these could introduce errors in measurement. You can be confident about the results from a validated method and well-maintained instrument. A thoroughly trained operator, applying his or her mind to the task at hand and through experience, can gauge the quality of the results. In spite of all this, an experienced chemist, a precise instrument, and a validated method, it's very hard to get the true value of measurement accurately. There are always errors and uncertainty associated with measurements. So what are these errors? Typically, there are 3 types of errors: determinate errors and indeterminate errors, as well as spurious errors. Determinate errors can be avoided if they are recognized. Unpredictable variations in repeated observations of the measured value is one example. You can reduce this error by increasing the number of observations. Indeterminate errors, on the other hand, exist by the very nature of measurement data. The analyst does not know their magnitude. These indeterminate errors affect the precision and accuracy of all chemical work. One example for this is the error due to inadequate control of experimental conditions. This can give rise to systematic errors that are not constant. These errors cannot be eliminated totally. However, we should attempt to contain them in as narrow a zone as possible. The other possible errors are termed spurious errors. These are mainly due to human errors or instrument failures. Whatever be the type of errors, we have to eliminate or minimize them. One way to minimize these errors is to make a series of measurements on the same object and report the average. So what is an average? When we do an experiment, we undertake measurements of few number of replicates and then calculate the average value from all these measurements. It is the sum of all individual measurements divided by the number of measurements. As you all know, average represents a central tendency wherein lies the true value. It is not an absolute value. It's only a point estimate of the true value. How can you estimate the true value? One way to do is through standard deviation, usually represented as S or sigma. Here, standard deviation is given by this equation, where X is the measurement value, X bar is the average value, and N is the total number of measurements. I said earlier, an average gives the estimate of true value. This is called point average. By using standard deviation, you can pinpoint the range within which this true value lies at a certain confidence level. The term confidence level, confidence interval, confidence limits, and interval estimates are used interchangeably. So you can express true value as X bar plus or minus 1.96 at 95% confidence, or X bar plus or minus 2.94S at 99% confidence. Usually, this 1.96S is rounded to 2S and 2.94S is rounded to 3S in practical terms. So we discussed about confidence interval, and so what is confidence interval? Confidence interval is a likely range of true value and is useful in expressing true value. There is another important concept in confidence limit it is also an estimator for precision. The wider the confidence interval, the less is the precision. We usually express the accuracy of results at 90% confidence, 95% confidence, or 99% confidence interval. So earlier I said you take an average of measurements. By taking average of measurement is one way to get an estimate of accurate true value. What is accuracy? Accuracy represents the closeness of the measured value to the true value. In this graph, the red line is intended true value. The green graph indicates the values obtained by the measurement. As you can see, the measurements are close to the true value and hence accurate. In the second graph, you have the red line is again the red line is a value that we obtained after the measurement. This is about 7.39 and it is not very accurate. Although down below you see that graph, it shows a fairly good precise value obtained in that. So now what is precision? Precision is reproducibility of the method. Here you can see the red line again is the true value that we got, and it has a very good precision because the measurement values are closely related to the true value. Here we got a fairly good true value, but as you see, the point measurements are scattered all over. There is quite a dispersion of values from this. So this dispersion or scatter is measured by average deviation, variance, and standard deviation. What is average deviation? It's represented by this formula here. Xi is the individual value, and X bar is the average value, N is the total number of replicates. The smaller the AD, average deviation, the more precise the measurements are. However, it is not an accurate measure of precision. So scientists use more commonly variance and standard deviation. Standard deviation is the square root of variance, and these all indicated spread of measurements around the data. And they do offer a better tool to measure the precision. Now, these are the terms that we introduced here, which you all know already, and we are going to use these to calculate uncertainty. So what is uncertainty? All the parameters like standard deviation or multiples of standard deviation shows a dispersion of results around the true value. This dispersion is the uncertainty around the true value. In general, the word uncertainty relates to the concept of doubt. The doubt is certainly not about the validity of measurement. In fact, the knowledge of this uncertainty increases the confidence in your measurement results. So it is, at this point, it is important to distinguish between error and uncertainty. A few slides ago, I had mentioned to you about various errors. Those errors, you can combine them to a single value. We cannot know exactly what the value is. However, we can estimate the uncertainty. So uncertainty estimation is simple in principle. As a first step, we should have a clear idea what is to be measured. Then you will write down all various processes involved in your measurement. You will be identifying sources of uncertainty within this process. Do you dilute the reference material? You write down the process. What is the sample dilution? What are all the environmental conditions? Is there any uncertainty associated with the equipment? You have to ponder over all these details and write it down in order to calculate the uncertainty. Once you know these components, you should quantify uncertainty from each of these within the process. Now, the information obtained in step 4 will consist of number of quantified contributions to overall uncertainty, whether they are associated with the individual sources or with the combined effects of several sources. This contribution is expressed as standard deviation and should be combined according to appropriate rules to give combined standard uncertainty. Once you have an idea about the combined standard uncertainty for the overall process, you would expand it by applying an appropriate coverage factor. There are two types of uncertainty. Type A is associated with repeated measurements, like when you do replicates in titration or an average value, average many readings in an instrument. So type A uncertainty is expressed as standard deviation or standard error of the mean. Type B, on the other hand, is based on scientific judgment, using all the relevant information available, including previous measurement data, experience, manufacturer specification, and data provided in the calibration report. There are 3 types of type B uncertainties. They are rectangular, triangular, and normal. To calculate the standard uncertainty from this listed uncertainty, we have to apply a normalizing factor for each of these. We will review these factors for each type. Now, the first type is a rectangular distribution. Rectangular distribution is used when uncertainty is stated without specifying level of confidence. That is, when there is no confidence interval stated, there is no reason to expect extreme values. So you convert the listed uncertainty for this by dividing by square root of 3, which is the normalization factor here. The second type is a triangular distribution. Here, the measured value lies very close to the target value. We use this distribution when we take into account uncertainty or tolerance given for volumetric glassware. For example, if you have a 500 ml flask, it is a class A, and usually class A have a tolerance of 0.2 mil for 500 ml flask. Now, the normalizing factor for this is square root of 6, hence to convert this listed uncertainty or tolerance to standard uncertainty, you would divide that by square root of 6. The third type is the normal distribution type. When we use this, when we make an estimate from repeated observations and express the results at certain confidence interval, it follows normal distribution. Examples of these would be a certificate of reference material that states uncertainty with certain confidence or level of confidence. Here, to convert the listed uncertainty to standard uncertainty, we use the coverage factor K if it is given, or if they just state a 95%, we would say we would use the normalization factor 1.96, and if it is stated at 99% confidence, we would use 2.94. So what we did so far, we determined the process, we outlined the process, we identified the sources, we calculated the uncertainty for the individual sources, and for now we are going to proceed to combine this uncertainty. There are two types of uncertainty we have here. One model is for the interim uncertainty. When the interim uncertainty is used for a particular component, say for instance, if you have a flask and you have a 500 ml flask, you have two components of uncertainty here, the tolerance of the class A volumetric flask as well as the temperature coefficient. Now you would be pooling these two uncertainties to give a total overall uncertainty for the flask. Then you would be proceeding further to determine for the flask that you have used, for the pipette that you have used, for the balance that you have used. So you will be writing all the uncertainties for the entire process. Now to combine all the individual uncertainty or the interim uncertainty to overall uncertainty for the process, you would use this equation. And here we have used the term relative standard uncertainty. Why do we use this? It is observed in chemical measurements, dominant contributions to the overall uncertainty vary in proportion to the level of analytes. Hence, it is sensible to use relative standard deviation when we combine each source. Then once you have combined the uncertainty for the overall process, now you have to expand it. Although the combined standard uncertainty is used to express the uncertainty of many measurement results, few regulating bodies require to define an interval around the result. The measure of the uncertainty intended to meet this requirement is termed as expanded uncertainty. This is usually done by multiplying by a coverage factor K. Coverage factor depends on the confidence interval and number of observations. K equals to 2 for observations greater than 7 at 95%, or K equals to 3 at 99% confidence. So finally, you would represent the true value as X equals average plus or minus expanded uncertainty, which is U. Now, these are the additional terms that we used in the preceding chapters: combined uncertainty and expanded uncertainty. These are all the important concepts in calculating the uncertainty for the process that I'm going to describe. So far, we have outlined the theory behind the calculation. Now, how do we take a practical approach to this? So what we did, we took gold pellets and dissolved it into solution with appropriate acid to make up volume. We analyzed it on our ICP, and the result was given 10,004 milligrams per liter concentration. Now, how sure are we about this concentration? So we go through all the steps I've said earlier, identify the uncertainty from each step, combine them, and expand them. So what is the review of steps I would use here? First, I have to determine what is to be measured. I'm measuring the concentration of the gold sample that I prepared. Then I will be outlining my process, which is going to come a little later. This process is dissolving gold in a sample solution and analyzing it ICP by comparing it with NIST SRM. So there are various components of uncertainty, sources of uncertainty for this particular process. So I will be identifying the sources. Now, once I have identified the sources, I will estimate the uncertainty for each source. Then I will combine all the components and expand it. So what is my process outlined for the analysis of gold? Now, in order to analyze my sample, I have to use the appropriate NIST SRM. So I prepared the NIST SRM, and the preparation of NIST SRM is given by the symbol standard P. And there are some components of uncertainty associated with my preparation. I weighed, I made up to volume, and then there is an SRM given, there is an uncertainty given in the certificate of SRM. So I would have to determine uncertainty from each of these components in order to find the total uncertainty for standard P. The next step I have is the dilution of my sample. This I represented as CRM F. Now this has two components uncertainty because I took a certain volume from a pipette and made up to volume in a flask. So there are two components of uncertainty rising from this for my CRMF. The third is I measured the concentration of SRM in ICP, and there is an uncertainty component associated with my measurement. A similar approach was taken for my CRM, and I measured the concentration of my sample, and that is the uncertainty associated with the CRM concentration here. So first and foremost, I have to determine my concentration. That's one of the goals. Now what is the equation I used? The concentration of gold in a sample is the concentration I measured from the ICP, the standard concentration that's prepared from the NIST SRM, and the dilution factor that I used divided by the measurement of the standard by my ICP. This is the ICP measured concentration. These values are plotted here, given here, and when you apply this here, you would be arriving at 10,004 milligrams per liter. How we arrived at these values is shown here. I will be explaining a bit later in my slides. Now the next goal for me is to determine the uncertainty. I have determined my concentration. Now I have to determine how sure I am about this concentration. So I have to calculate the uncertainty associated with the process as a whole. So what are the components of uncertainty here? This gives me the one component, that's preparation of the standard, represented by standard P. Here I weighed it, so there is a mass component, and I made up to a certain volume, so there is a tolerance component for the flask and temperature component arising from coefficient of expansion of the liquid in the flask. Then the SRM certificate came with uncertainty already, so I have to factor that into this. Then next step is sample dilution. I prepared the sample in order to analyze in my ICP instrument. And there are two components here. One is the pipette uncertainty, and that has two components, tolerance of the pipette and temperature due to coefficient of expansion of the liquid. And then I have the flask component, which is, again, it has a tolerance and temperature component as the pipette. So combining all this, I will get the uncertainty for my CRMF, sample dilution. Then I measured the concentration by ICP, and this represents the uncertainty due to ICP measurement for SRM. Again, similar process was taken for the ICP measurement for the sample, so that component has to be concerned. So now you have 4 major components and very many minor components to each of these 4 major components. So usually it is better to represent all the components by means of this fishbone diagram. This gives you a better idea how to proceed. Now first we are going to calculate the uncertainty associated with standard. We used NIST SRM 3121. We prepared, we weighed about 5.067 grams in a balance and diluted to 500 ml flask. So as I said in my fishbone diagram, there are 3 components of uncertainty grids. Weighing on the balance, making up to volume in 500 ml flask, and the certification that SRM has given me also had some uncertainty. So I have to factor all of these to calculate the total uncertainty for this process. So let us take first weighing on balance. In my balance certificate, when I examined, the calibration was given, but it had not stated any confidence interval. So I would use a rectangular distribution in such a scenario. So the value was 0.0001 gram, and I used the normalization factor √3 and arrived at 5.774, 10 to the power 5 as my uncertainty. Now I have used a tare weight and then used the gross weight in order to measure this 5.067 grams. So I have uncertainty twice the amount. So I listed it, I pooled it, and that value is given here. So what did we have now? In this table, we have the uncertainty, the value, which is 5.067 grams, the uncertainty that I combined and I found for this balance. Now I have to calculate relative uncertainty, which is combined uncertainty divided by the value. This is what I'm going to use later to calculate my overall uncertainty. So we did the calculation for weighing on balance. The next step is making up to volume in 500 ml flask. There are 2 uncertainties associated with dilution. One is the tolerance given for the flask, which was 0.2, and since it's a triangular distribution, as I have mentioned earlier, for volumetric glassware, you use a triangular distribution. So you normalize it, and to calculate the standard uncertainty from the listed uncertainty, you would use the tolerance divided by the normalizing factor, and you got about 0.08165. The next contribution is from the liquid that is in that. Usually it is water. So thermal coefficient of water, external expansion is 2.1 10 to the power of minus 4 degrees Celsius per ml. Ours is an environmental control lab. Still it had a variation of 3 degrees Celsius in our lab. And then the volume coefficient for this is 500 ml. So when you factor all this and divided by the normalizing factor √3 for rectangular distribution, you get a value 0.1819. So how do we pool the uncertainty for the 500 ml flask? That is U due to volume and U due to temperature. So when you pool this, you get this value. Now, this is the interim uncertainty. Now we have to find the relative standard uncertainty to use in our overall process. So for a 500 ml value, our combined uncertainty was 0.19935, So the relative uncertainty was UC by B, and that is the value given here as 0.0003987. So we did, for this standard P, to calculate the uncertainty for standard P, we did two components already, weighing on balance and the volume component due to 500 ml flask. Now there is a third component, SRM certification. SRM certification had the certified value for gold at 9.89 milligram per gram. It had an expanded uncertainty of 0.02. The coverage factor stated there was 2. So you have to convert that to standard uncertainty. You divide the uncertainty given in the certificate by 2. So you arrive at a value of 0.01. Now you calculate the relative uncertainty for this approach, and you arrive at a value 1.011 10 to the power minus 3. Now, putting it all together, the uncertainty component from balance, from the flask, and SRM certification, putting it all together, you got a total value of 1.1816 10 to the power minus 6. The next uncertainty component, major component, was our CRM dilution. So what did we do here? We took 5 ml sample and diluted it to 500 ml. So there are two components of uncertainty here. One is from the pipette and other is from the flask. Just as similar to the earlier calculation, the listed U for the pipette was 0.01, and it's a triangular distribution, so we normalized it by square root of 6. We arrived at the value 0.004082. Now again, it has a temperature, liquid coefficient expansion of water should be used. So for that, the same expression we used. Our temperature variation was 3 degrees, and the volume that we used in the pipette was 5 ml. And when we normalize it by square root of 3, we arrive at this value. So now we have to pool the uncertainty for the pipette. So that is U tolerance plus U temperature. When you pool it, you get a value 0.004469. Now you find the relative uncertainty by dividing the value 5, and you arrive at this value 008938. So we finished the calculation for uncertainty for the pipette. The next task is to calculate for the flask. For the flask, we used a 500 ml class A type. So the listed uncertainty was 0.2 ml. The normalization factor, this is triangular, so we use root 6. The value, when you convert it to standard uncertainty for U tolerance, is 0.8165. Now again, this also has the liquid coefficient of expansion of the liquid component to it. So similar equations used. Here, the volume is 500 ml. Temperature variation was 3 degrees. So you normalize the whole thing by square root of 3 and arrive at a value 0.1819. So now our task is to pool the uncertainty for the flask from their individual components like U tolerance and U temperature. So this is the value you get for the flask. Now, relative uncertainty for the flask is given here as 0.003987. So what do we have now for overall uncertainty for CRMF? Pipette uncertainty, where relative uncertainty is calculated to be 0.008938. Flask uncertainty, the relative uncertainty is calculated to be 0.003987. And the total uncertainty is given here. This is the value we are going to use later in pooling the overall uncertainty for the method. Now the third component that we saw in the fishbone diagram was calculation of the measurement uncertainty by ICP. We took 9 different samples, analyzed them, and we found an average of 100.985 by the ICP measurement. The standard deviation for the whole process was 0.29397. So this is a type A uncertainty, and so you would apply this equation, and you arrive at the relative standard uncertainty by dividing the combined uncertainty by the value 100.985. So this also will be used later on in our process. Now, similar to what we did for SRM, we did for CRM. We took 9 samples, made analysis on that by ICP. Now, the average is given here, X bar 100.797. The standard deviation is 0.3065. Now, this again is a type A uncertainty. So the value of uncertainty calculates out to be 0.102165. And this is the standard deviation divided by the number of replicates, and we arrive at this 0.102165. So you calculate the relative standard uncertainty by dividing the uncertainty by the value here. So now what do we have? This represents uncertainty from each component. As you had seen, uncertainty for SRM prep had its own components. We pooled uncertainty from each of those individual components, and finally we calculated as for standard P, the relative standard uncertainty. We took a similar approach for sample prep, and there were quite a few individual components to this, and we pooled that and we got this value. Now, so the uncertainty for SRM measurement is pretty straightforward, and same thing for uncertainties for sample measurement. Now, the total uncertainty is sum of the squares of all these relative standard uncertainty, and that's given here. So finally, the uncertainty for overall process is square root of this and is given here as 0.00202697. Now, we determined the concentration of the gold as 10,004 milligram per liter. Now, we multiply that by the uncertainty here. So the overall uncertainty for the concentration that we have in our flask is 20.2771. As I have mentioned earlier, the uncertainty measurement just doesn't stop at combining them. You do have to multiply by a coverage factor and expand them. So here we use a 95% confidence interval and a coverage factor of 2. So when you do the multiplication here, you got a value of 40.554, and we rounded up to 41 milligrams per liter. So our ICP value for gold is 10,004 milligrams per liter, plus or minus 41 milligrams per liter. So the gold bars you saw earlier might have had some uncertainty component. It's not 99.999 as you would think. It has this 41 milligrams per liter as uncertainty associated with it. We have taken all this information from the references given here. Our aim here is to determine uncertainty in the analysis of sample we prepared. Analytical parameters and conditions for analysis are not presented, but then it varies from lab to lab. We have tried to give an overall approach, and this could vary from process to process, lab to lab, and it's by no means comprehensive. So you have to determine what you have and then continue the process that I have mentioned and pool it. So I hope I have demystified the whole process and you're able to calculate uncertainty without any problem in future. If you have any problems, of course, you're always welcome to contact SPEX CertiPrep. Thank you for listening to our talk. We are planning a few more additional information. Here what we did, we focused our attention only on the analysis by ICP. And by no means a CRM is restricted only to the analysis. You have uncertainty due to sample preparation. You have uncertainty due to the homogeneity, stability, as well as any methods that you use to compute your certified value. I have not gone into details of all the other things because I'm planning to save that for your additional seminars that we are planning here. Hope you enjoyed this seminar. Thank you, Peter.
Okay. Thank you, Vanuja. We've got a little bit of time for questions, so I don't see any up front at the moment. But if you have any questions at all, just type them into the question box, and we'd be more than happy to answer them. Okay. Looks like we have one here.
Okay. The question here is, why do you use relative standard uncertainty in some cases and not in other cases? I told you there are two processes involved in calculation here. One is the interim calculation, and another is the combining the interim uncertainties to the overall calculation. Whenever there is an interim calculation, we calculated the component from each of those as they are. Then when we combined it to an overall process, then we took the relative uncertainty, so standard uncertainty. It is because usually in chemical measurements, contributions to overall uncertainty vary in proportion to the concentration or the level or the value measured. So it is sensible to use as RSD, relative standard deviation, when we combine the uncertainty from various sources to one process.
I've got a couple questions here about whether or not we're going to give out the slides. And yes, we will be sending out an email a little later today with a link so that you can download the slides. And also, another person is asking about recordings of the webinar. And yes, this webinar is being recorded. And sometime next week, we'll post it on YouTube. We'll also send out an email letting you know when that's available. All right, we got another one here. What would be your approach on qualitative methodology, such as the ones found in microbiology?
Okay, I repeat the question here. What would your approach be on qualitative methods as found in microbiology? As I said, you have to be familiar with the methods, and I'm not familiar with this method, but you can use the same methodology that I have described here. You would outline the process, identify the sources, and then you will calculate it. You have to be familiar with the method in order to do this.
Another question, what is coverage factor?
The coverage factor is usually called K, and as I said, some of the regulation indicate that you have to have a central value flanked by a plus or minus value. That is, especially with the health and safety regulations, there is no absolute true value, so they want an interval value. So when you calculate the method uncertainty, you expand it by 2 in order to flank your absolute value by that expanded uncertainty. Well, there is another question here. What if there are other sources other than I had listed, such as fill-in volume? I think by fill-in volume you mean delivery of solution from the volumetric flask. If that is so, what you have to do, we did some experiments here. Before proceeding to quantifying the uncertainty, we considered many factors, and then we calculated uncertainty, and we used a bar graph to determine how significant that particular component is to the overall uncertainty. If we found them to be not very significant, then we omitted it. That's because otherwise the complications get, the complexity of the calculation gets too hard, and you are not able to get a real practical input into that. So what I would do, in anything you want to do, first go through the process, determine the uncertainty, and see if it is really significant, significantly contributing to your process. Then you would consider that.
Okay, another question. I usually deal with rock powders, silicate rocks, that are digested for ICP OES analysis. From your experience, are errors usually higher than dealing with single element standards or samples?
Yes, absolutely. The rock samples, as you know, they are not homogeneous. You may get various sample composition, and so you don't know what you are getting at. So even if you have, when you dissolve a certain amount of rock, when you dissolve the rock, and then you may want to do 2-3 replicates to see if your value is good. There is one more problem you may have here. Rock samples have various matrices, various components, and you will not be able to recover it completely. So what we usually do in such cases, we do a spike recovery, and then use the spike recovery as a type A uncertainty and compare it and then add it to this particular process.
Another question here. When trying to calculate uncertainty for probe analysis, which is better to use?
By probe analysis, I think you mean any pH meter, conductivity meter, that type. If that is what you mean, there are, again, you have a sample uncertainty due to sample preparation. Whatever sample you prepare to analyze, you have to take into account, as I have mentioned here, by this process. Then you would take various readings and compute the readings as the type A uncertainty and then calculate it. Unless we know the process completely, I won't be able to say exactly what you do, but I think from what I understand from your question, it is the overall approach I would take.
Okay. What is the percent total uncertainty of the gold measurement? I guess from the example you just did.
Yes, it's about 0.4%.
Do you know which type B uncertainty to use for the flask, balance, or pipette?
Yes. Usually for the volumetric flask or the glassware, we use triangular distribution, which is normalizing factor is √6. For the balance, there are two approaches here. Some calibration agencies, they do not give the confidence, they do not state the confidence level. If there is no confidence interval stated in the calibration certificate, you would consider that as a rectangular distribution and use the normalizing factor √3. But of late, many of the agencies that I have used have started giving the confidence interval at 95%. Then I would use the coverage factor K = 2 or 1.96.
Do you consider stability into the uncertainty?
Yes, we usually do for our reference materials. In this particular case, I didn't go to that because my focus here is to calculate the uncertainty only by the instrument method. Then, as I said, we are planning a few seminars on the overall uncertainty from the sample preparation, the purity of the salt, or the stability and homogeneity. In that, we will cover all those other aspects as well.
See another one here. How do you estimate MU when this change with the concentration of the measurement?
How you estimate measurement of uncertainty when this change with the concentration of the measurement? Yes, that is why we use relative standard uncertainty. This is exactly why we use relative standard uncertainty to calculate.
I believe we got to all the questions. Looks like we covered everything. So if there's, we got a few more minutes here. So if there's anything else that you want answered, please type it in, and we'll certainly. Oh no, we got a couple more.
The question here is about the number of observations minimum needed to use the coverage factor 2. Yes, the coverage factor to minimum needed is about number 7. Because the K = 2 is used when the degrees of freedom are 6. If it is less than 6, if you have observations less than 6, then what do? You have to use the two-tailed students T at 95% confidence. Usually, with the decrease in number of measurements, you get a greater uncertainty. That is why we tend to use about 7 measurements of 7 or observations of 7 or more in order to reduce the uncertainty.
There's a question that's related to that. What is the appropriate N numbers needed when using the standard distribution curve at, say, the 95% confidence level? Is it a minimum of N equals 9, as you stated, or the more the better, like N equals 20 is ideal?
No, there is a statistical approach. How many minimum replicates are needed in order to arrive at a good value? What is the most benefit you get? Did you get, by increasing the number of measurements, do you get a better value? No. I think they have decided, this is a calculation available. If I can find it, I will send it to you. Minimum is greater than 6, replicates greater than 6, does not increase any benefit in the accuracy.
And how does one find K, or the coverage factor?
If your observation is less than 7, you go to the students T. Students T, it is available in any statistics book, or I can email you that.
Okay. Okay. It looks like that's about it again. So again, we still have a couple more minutes, so feel free to type it in. I've got a few more things that I can cover while we're waiting for you guys to type it in. So if you haven't already received a copy of our new catalog, then you can request or download it right from our website. You can choose from the paper version, CD, or view the electronic flipbook. We also recently launched a consumer safety standards product for the manufacturers of pharmaceuticals and nutraceuticals that must comply with USP 232. And SPEX CertiPrep is social, so come visit us on your favorite social networking site. We have pages on Facebook, Twitter, YouTube, LabRoots, and LinkedIn. And anyone who is interested in any of our previous webinars, including BPA and phthalates and consumer products, clean lab techniques, or the art and chemistry of wine, can watch them right now on our YouTube channel at youtube.com/SPECCertiprep. Okay, Vanuja, thank you for giving us yet another great presentation. As a reminder, we will be sending everyone a copy of the presentation slides, and the recording of the webinar will be posted in about a week or so. We'll also send an email out for that to let you know when and where to view it. I'd like to thank everyone for attending today, and we hope you are walking away with a better understanding of uncertainty and how it relates to instrumental analysis. We appreciate your time. Look forward to seeing you again in a future webinar. Thank you.